All right, good afternoon, everyone. It's my pleasure to introduce Chris. Sorry, Christidis. Who's kindly agreed to step in for our original speaker, Mike Martin, who unfortunately couldn't make it today. So thank you very much for that. Chris received his master's degree in structural engineering from Ryerson University, which is now Toronto Metropolitan University. He's very well connected within the concrete industry. He is the acting Ontario chapter president of the American Concrete Institute. And he also works as a technical representative of materials. So with that, thank you again for coming. And please, the floor is yours.
No problem. Thank you very much. Off at the end if you like the presentation. All right, so I understand I have a wide group here that different competencies in civil engineering. We're going to be talking about, I guess, concrete basics to some extent. I'm going to go from as technical as I can be, which I'm sure you guys are more technical than I am, to, to this as simplistic as I can be as well. So if you have any questions, don't hesitate to raise your hand and throw something at me or whatever to stop me, and we'll answer your questions. So first off, in Canada, this is a breakdown of how much ready-mix concrete is produced in all our provinces. And you'll see that the #1 province, Ontario, produces about 35% of all ready-mix concrete in Canada. And then you'll see the breakdown all the way through. It's not surprising because our population in Ontario is pretty big. So you can imagine that we would be producing the most amount of concrete. In fact, if you were to look at Toronto 5 years ago, maybe about 5 years ago, was it 5 or 10? We had, I think we had one of the world's most amount of cranes in that city at that time. So we're doing a lot of work in and around Ontario. If you break that down even further, you'll see that we produce about 11 million cubic meters of concrete every year. There are 270 concrete plants within Ontario. All those concrete plants, each one of those concrete plants has concrete trucks, and there's about 3,800 of those. And then you can see about the number of deliveries that are from those trucks. So each truck has about 8 or 9 meters of concrete, so that equals the 11 million, if you look at it that way. If you look at how that breaks down in the concrete industry or the market itself, the concrete industry, the biggest amount of concrete goes into the industrial, commercial, and industrial, commercial, and the other I, which I can't remember right now.
Industrial.
Say again?
Industrial.
Yeah, industrial, commercial, and
Residential.
institutional. Someone got it. There you go. Thank you. This is the kind of presentation we're going to have. Everybody's going to participate. All right. And then we got the residential and condo has 30%. And then you can see how the rest breaks down, right? So what is concrete? You guys all well know what it is, but we'll go into that a little bit. It is a man-made rock that can be shaped infinitely in any shape that you want to kind of create out of it. It's flowable, so it can be you can create any type of shape that you want. It has structural elements and it has aesthetic elements to it. So it's actually one of the most versatile construction materials you can use today. So what exactly are we looking for when it comes to concrete for construction? Well, it has a great compressive strength, but it's weak in tension. So you usually see concrete combined with reinforcement in order to compensate for the fact that it's weak in tension. The raw materials in concrete, you have Portland cement, aggregates, water, and admixtures. And these are kind of changing slowly because of new requirements on CO2 and just new innovation that's coming out, which I'm sure some of you guys are even studying today or working on in your theses. that can be used to almost maybe add another category or at least add to whatever's going on here. For example, I know cement is a hot topic right now for CO2, so that might change in the future, and it may not be Portland cement, it might be some other, type of cement that will be available. How does that break down? Yes, concrete has air in it. Regardless if you try to entrain it or not, it's going to have either 2% or 6% or 9%, usually nothing higher than that, unless you have a flowable fill, which you could have even more. And then you have 11% is Portland cement. Keep that in mind for later, because 11% of Portland cement and at the same time, Portland cement is the biggest contributor in CO2. So the fact that it's 11%, but it's the biggest contributor to CO2 is pretty pronounced. Then you have the aggregates that go in, the stone and the sand, and the water at 16%. The types of stones that typically are used in ready mix production. You've got crushed limestone and silicious gravel. You don't typically see other types. Trying to think about, I mean, you might see something in a heavyweight concrete that doesn't follow these two main ones, but these are the main ones that will be used in ready mix concrete in Ontario. Cement basics. So the main contributing factor, or one of the contributing factors to the high CO2 content of cement is the fact that you've got to heat it around 1100 to 1700. I think it's around 1450 actually is the target for most cements. That heating of that cement is what causes a lot of the CO2. And then you grind that all up and you create a cement you create a clinker, and that clinker is ground up and you add gypsum to it to make your cement. These are the different types of cements that exist. The bottom four are very rarely seen. Oh no, sorry, HE is seen. This one, moderate sulfate resistant, low heat hydration, and high sulfate resistant cements are rarely seen. GU is disappearing slowly in the industry. It's becoming GUL. GUL just means more limestone in the percentage of cement. Where they used to be below 5%, so you typically see a 3 to 4% limestone filler mixed in with the Portland cement to give you a GU or type 30 or type 3, depends on how you call it, where you are. Now you see below 15%, limestone mixed in with the cement, and the reason why they do that is to reduce CO2. So by doing that, you're basically, I mean, the math is pretty simple, considering that I just said this is about 5 and this is about 15, while you're reducing the CO2 by 10%. So that kind of all makes sense why we're going in that direction. Moderate sulfate resistant type 2 or type 20, you don't typically see. I've actually never physically seen this in the industry. They usually achieve this by adding slag or fly ash or something else. You don't need type 20. High early, it still exists. A lot of precasters will use high early. And yeah, it's one of those that you'll see. It's going to slowly start disappearing and becoming an HEL, which again, just like the GUL, is going to contain a certain amount of limestone filler. And then you have low heat hydration and high sulfate resistance. And again, these are typically replaced by supplementary cementing materials, which we'll go into later. So these are supplementaries. You've got slag, which is a byproduct of iron blast furnace. It is this is the most amount. This is the one that we use the most in Ontario, slag. Fly ash is slowly disappearing just because we don't really produce coal burning plants anymore, because those are slowly disappearing. And silica fume, you still see this, but it's a little bit hard to work with, so you don't see it as much as a supplementary as you would slag. And even slag itself, within the next couple, I think they're predicting 10 to 15 years, we're slowly going to be depleting that as well. So that's going to start to disappear. Fly ash is probably heavier out west in Canada than it is in Ontario. And yeah. How many of you have already seen this kind of stuff before? Okay. Okay, so we're on pace, we're good. I'm not boring too many of you, right? Okay, good. So supplementary cementing materials is exactly as the word calls it. It's basically you're taking a portion of cement out of your mix design, out of concrete, to replace it with something that can replace the cement and still give you some benefits. Those are the supplementaries we're talking about over there. We have typical replacement rates, depending, this is typically fly ash and slag. Silica fume could be 5%, 4% I've seen, 7%. It doesn't typically get up to 10% simply because the mix becomes very sticky and difficult to work with. And most people don't want to work with that type of material. So these are numbers really for fly ash and slag. And even fly ash doesn't go up to 50 usually. It goes below 30% if you were to see it out there. Slag can go up to 50. I've seen slag up to 75. It depends on what your application is. Why do we use supplementaries? Well, they improve workability. They reduce the heat of hydration. They improve durability. They increase strength long term. They prevent or they reduce alkali silica reaction. And unfortunately, you need to increase the curing time when you use a supplementary, just because of its strength development and how long it takes for it to actually react. A little bit of cement knowledge here, chemistry. The hydration occurs when you mix Portland cement and water together. They get calcium silica hydrates plus calcium hydrates. Supplementary cementing materials cannot produce calcium silica hydrates on their own. And that's why you can't just use that to supplement cement. They need the calcium hydrates here in order to, well, guess what they're providing out of this whole equation here. So the calcium hydrates, the supplementary cementing material and water, you're missing one component to give the calcium silica hydrates. That's what the supplementary provides. And you get calcium silica hydrates. And that's how they function in the cement side of things. I'm going to skip that one. So the effects of supplementaries in plastic concrete, you will have longer curing times, which is something you have to deal with in the field. So when they're building buildings, you have to take that into consideration. Your heat of hydration is reduced typically with fly ash and slag. With silica fume, it can often stay the same or increase the heat of hydration. The heat of hydration is how much heat is being produced when that chemical reaction of cement is occurring, and you get a certain amount of heat that gets produced by that chemical reaction. Then the setting time, usually slag and fly ash will retard the setting time, and the final set. Silica fume may have no impact on setting time, or it can increase, or it can decrease setting time, or it can actually increase. It's kind of in between. It depends on how much you have in there and how fine it is and a whole bunch of other things. SCMs typically help with pumping. And this is like a really key one right now. And it's like what the industry is really talking about is greenhouse gases. The government of Canada has mandated by 2030 that we're going to reduce the amount of CO2 in specifically in concrete or in the industry in general by 50%. And so by 2050, they're expecting a net zero CO2 content. So that's a very big topic right now in the industry, and they are already trying to develop ways of trying to get concrete down to net zero. So supplementaries help with that. Because they're a byproduct, they're considered zero in terms of CO2 because it's a recycled material. The only part where CO2 comes into play is by transportation, because you have to transport it from whatever plant to the other, and that increases the amount of CO2 it has. But it typically is a lot less than cement. And that's what you'll see here. Admixtures. So what you're seeing in pictures here are just different colors of admixtures. Anyone know why they changed the color of the admixture? Not the original color for all these things. These are mostly clear. Go ahead.
Just distinguish them, basically.
Yeah, so when the driver comes and delivers, he knows I've got blue, that's purple or pink. But that's really the only reason why they do it. And also it looks cool. The only reason. So that's exactly why they do it. This is a typical system you'd see for actually pumping admixtures into the plant. So it's all liquid based and it goes through hose and meters and such to get up in there. If you were to go to ASTM C494, you'd see a definition of different types of admixtures that exist in the industry. Water reduce, they basically do as the naming says. Water reducing is an admix that would reduce the amount of water you need to get the same slump. Retarders, we'll go into a little bit of retarders and accelerators in the next slides. But they are, you'll understand that shortly. And then you've got a combination of different types of water reducing, retarding, water reducing, accelerating, high range, so forth and so on. We do add air into concrete. We add air, we'll go into that a little bit later too, to help with its durability and its survival in our winters. If you want to increase the workability of the concrete, we add superplasticizers. They're also a whole slew of different admixtures. For every problem concrete has created, let's say, there are admixture solutions to those. So why am I saying that? Because we need to add steel into the concrete in order for it to be viable, so that because of its tensile strength. Well, there's an admix that helps avoid the corrosion of steel in the concrete. Hydration stabilizer. Let's say you need to deliver the concrete 3 hours away from the location where it's made or where it's mixed. You add a hydration stabilizer to give you that distance so that it doesn't harden in your truck. Shrinkage reducing. Concrete tends to shrink. You're going to get a considerable amount of shrinkage. You can add a product that helps reduce the shrinkage that goes in the concrete. And because it's an architectural product, you can also change the color of it. Not everybody loves gray. Some people want pink. Whatever floats their boat. High range water reducers. The idea of a high range water reducer or superplasticizer is to help reduce the amount of water that you need in the mix, but maintain your slump. Or it helps you increase your slump in a mix that already has a specific amount of water in it. That's the purpose of those products. Now, why do we care about the amount of water that goes into the mix? I'll tell you in the next slides because it's not where I thought it would be. We have accelerating admixtures. Accelerating admixtures are exactly as they say they are. They help accelerate when the set time of the concrete occurs. So, like I said, when you add Portland cement to water, you get a chemical reaction. That chemical reaction can be impacted by temperature. If you end up putting concrete in colder climate, you're going to increase the time it takes for that reaction to occur. You're going to increase setting time and initial set and final set. Those are important parameters because initial set is usually when a floor finisher will get on top of your concrete and finish the floor. Final set, they're already too late. Most times they're not really doing much after that. So they have a specific window that they can go on top of the concrete and finish it to make it nice, smooth, and finished. So that's why we play around with these parameters so that the floor finishers, if you guys have ever been on site, they like to complain a lot. So we don't want them complaining. That's why we added an accelerator. Okay. It helps in two ways. One, it will speed up when that set time occurs. Let's say that they're trying to get traffic on the 401. I've actually done a job like this. We're trying to get traffic on the 401. That concrete has to set within an hour or two before traffic goes on top. So you need to set it up in an hour or two. You'll add an accelerator. Concrete doesn't naturally set up in an hour or two. If you're doing it in cold weather, again, the same thing, it will help you adjust that set time so that it sets at a normal time rather than delayed or accelerated. There's two types of accelerators, non-chloride and chloride accelerators. Why do we not use fluoride accelerators in reinforcement? You're too smart, man. Go ahead, it's an easy question. Go ahead.
Yeah, because chloride, what they call it, corrodes the reinforcements basically.
Exactly. So you got to have two types of accelerators. Why, if this one is no good to use in reinforced concrete, does this even exist? What?
Or sidewalks, maybe? They don't put reinforcement in the sidewalks.
Not exactly.
Is it cheaper?
There you go. That's the reason why. They do use, you're right, they would use calcium chloride in sidewalks because there's no reinforcement in sidewalks. But really the whole thing is it's cheaper. It's much cheaper than a non-chloride. That's it. Simple. It was a trick question in a way. You were trying to look for this, fancy answer, but no, it's just as simple as it's cheaper. Okay. Retarders, they do the opposite of an accelerator. If you are in a hot weather condition and you're trying to make sure that the concrete doesn't take off too quickly so that the floor finisher can get on top of it, you need to add a retarder. It slows down the reaction so that the finisher can get on top of the finisher. That's one use. The other use is maybe you want to retard the concrete for a certain amount of time because you have a large pour, for example, and you have a bridge deck and you have this large pour and you don't want pour lines. You don't want to have cold joints. You don't want to have the problem with the two concretes kind of combining together and connecting. Well, you can retard the concrete. And I've actually seen projects where they'll start with a concrete that's expected to retard for 15 hours. And then they'll keep reducing the amount of retarder that goes in so that by the end of it, it all kind of tries to set at the same time. Because we can only deliver concrete at 8-9 meter loads. And you might have a big project that requires 50 meters. You want to try to get it all to set at the same time for whatever reason the project is requiring. So that happens too. Water needs to be potable, and you can use recycled water as long as it's been tested. I've seen precast plants use well water that smells like sulfur. You think it's not good. They've tested it. It's fine. It passes, and they use it. I wouldn't drink it though. We hit on this a little bit earlier. Hydration. So hydration is when the water and the cement start to react, and it require a certain amount of water to hydrate. That whole process is actually called the hydration process. It is temperature and time dependent, and like I said earlier, it's a chemical reaction, so it produces a certain amount of heat. So high cement contents will. So why would we want to worry about hydration, heat, for example? So the next slide is going to be talking a little bit about heat and hydration. Why do we worry about that? Anyone know? Go ahead.
It did not raise the water actually.
Yeah, it can do that. Yep. Any other reason? Because there's a thing called thermal cracking. You can have the concrete in the center heat up too fast, and the outsides are cool, and it will crack the concrete. It's a differential in temperature, and they will crack the concrete. So that's why we kind of want to control heat of hydration. And you can see here that too much cement can cause a greater amount of heat of hydration. Makes sense because that's the thing that's reacting, that's creating heat for you. If the concrete's too thick, it can have a greater heat of hydration. Why is that? Anyone know? If the concrete's too thick, it doesn't dissipate fast enough. So it takes time for it to actually get, and for the heat from the center of the core of a 1 meter pour to dissipate and reduce the heat of hydration. So that's why thick concretes have higher heats of hydration. SCMs reduce the peak temperatures just in the way that they actually react with the cement to create this calcium silica hydrates. It's a little bit slower process. And so it ends up reducing the temperature that gets created. And then most people will know that concrete usually has a 28-day requirement. This is if it doesn't have high SCMs. If it has high SCMs, the engineer might say 56 days or 90 days. It depends on the project. But 28-day is usually the target for concrete. And the reason why that target exists is because most of its strength occurs at that time. Another interesting facts you might want to know is that concrete will stop gaining strength if it dries out, because the cement won't be hydrating anymore with water, so it stops its temperature of the concrete can also change the rate of hydration. Anyone know if there's a temperature that concrete will stop reacting? Yeah, do you know what temperature that is?
I think between 5 and 0.
Yeah, 4. It's around 4. You're right. So if you get around that temperature, concrete itself, and we're talking about the concrete will stop hydrating, will stop actually reacting. So that's a good thing to note. Anything here I really want to show you? Heat hydration time. The real kick for heat hydration happens after initial set. And if initial set is defined as, when you do a penetrometer test, it's defined as 500 PSI. So when you do a test on it, you get 500 PSI, you hit initial set. Final set is defined as 4,000 PSI when you do that penetrometer test. Okay, so that's the concrete strength to give you those initial and final sets. And you'll see that when it hits initial set, that's when it starts to skyrocket in hydration. When it hits final set, that's when it starts to actually calm down and come back and slow its the heat hydration down until it gets to like a steady state. So under higher temperature effects, what happens? Concrete will start to gain strength considerably. You'll start to lose your slump considerably. And your set time will decrease. Make sense so far? What you might not know is that a higher initial strength, you'll get a higher initial strength when you heat your concrete. Oops. You get a higher initial strength when you heat your concrete, but you'll get a lower ultimate 28-day strength. And that has to do with the chemical process. It has to do with you're gaining more tricalcium silicates in your first 7 days with the higher temperatures than you are the dicalcium silicates. And that is what gives you your initial high strength. But the dicalcium silicate is what gives you your ultimate higher strength down the road. So you can see set time differences depending on the temperature. So concrete at 20, if the concrete temperature is 32 degrees Celsius, you'll see two things happen. First, the initial set happens sooner than a typical concrete at 23 degrees Celsius. And then the other thing you'll see is that initial and final set are relatively close together. When it comes down to colder temperature concretes, initial set is slower. Final set and initial set difference is probably here in this case, for example, is 2 hours. In this case here, it's about a half an hour. And the initial case here might be about an hour, for example. So why would that be a problem? Because your floor finisher means here, he or she needs to work their buns off to get that floor finished. And they're never happy about that. Whereas in here, they have 2 hours, yes, but they might be done in 45 minutes, and then they're twiddling their thumbs until, you know, you get your final set. So they don't want that either. So you kind of want, it's kind of like the story of the three bears. One is too soft, one's too hard, and this one is just right. That's the kind of the setting time they expect, and that's what they want you to give them. Low temperatures is the reverse. The thing I'll note here is that your 7-day strengths might be a bit lower with lower temperatures. However, your 28-day strength, again, it has to do with the tricalcium and dicalcium silicates. Because you have a longer time, the dicalcium silicates can form, which gives you higher strength at 28 days. All right, so we got two components in concrete. We have the binder and we have the building materials, or the paste. which is water, cement, and admixtures, and the building material or the binding materials is fine and coarse aggregate and rebar. It could be other things too. It could be steel fibers. It could be whatever fantastic theses you guys are working on that you're trying to incorporate into concrete. They're looking at things now in the industry like graphene is starting to become a little popular. There's different materials they're looking at to try to add to concrete to make it either lower CO2 or cheaper or better in performance. Water cement ratio is what impacts your concrete strength. It's pretty much your, as long as you have good aggregates, it's pretty much your the key function for a lot of things in concrete. For example, it impacts your compressive strength, it impacts your permeability, your shrinkage and cracking, it can impact that. And again, this one's like the three bears. If you have low water cement ratio at around 0.32, then you're gonna get something called autogenous shrinkage. If you get something like 0.8 water cement ratio, you're gonna get drying shrinkage in your concrete. Those are gonna be the major shrinkage factors. Abrasion resistance, the lower the water cement ratio, the more abrasion resistant the concrete is. Permeability has to do with the fact that if you have a high water cement ratio, basically you have these crystals that are forming. And if you have a high water cement ratio, it would be here. The lower the water cement ratio, the crystals start to really bind together and you don't have a lot of space for the water to travel. Plus that water that's in there goes somewhere when it dries and it creates channels. So that's why the permeability changes. Go ahead. Sorry, you asking a question? Oh, okay. Air and trained concrete versus non-air and trained concrete behave the exact same way. Non-air and trained just means that it has the standard 2-3% of air that is in concrete already that's entrapped. Air and trained usually means somewhere between 4 and 9%, depending on the spec. Of course, you're going to get a little bit of a strength decrease with air and trained, simply because it is air. You're adding air to the concrete. It's got no strength to it. So that's why you'll see a bit of a strength loss. So the advantage of using lower water cement ratios in concrete, you get increased strength, lower permeability, as we just talked about. Resistance to weathering, freeze thaw, yes, because of the low permeability, because of the increased strength. Better bond between the concrete and the reinforcement, usually, depends. If it's too dry, it's not, that could be a problem as well. If you have proper consolidation, that's going to be a problem. Can do reduce drying shrinkage here? Yes. It's going to increase autogenous shrinkage though. So there is a limit for drying shrinkage. It's around 0.4 water cement ratio. And then there's going to be less change in volume when you wet the concrete and dry the concrete. Okay, so these are kind of the increase. The only difference here is that you'll have bleeding as you increase your water cement ratio. Bleeding is the water that comes to the top that's not been bound to the cement particles. That is going to that water is going to come to the surface, and too much bleeding is never a good thing for the floor finisher. We really care about that floor finisher actually, because we want that person not to get too angry at us. So bleeding is important. They don't want to have too much bleeding. They don't want to wait for the bleed water to disappear before they can finish the surface. No bleed is also a bad thing. It's usually means it's a pretty sticky concrete. They want a little bit of bleed, but not too much. That's what they'll tell you. And then you ask them, what does that mean? What does a little bit of bleed for you mean? Yeah. Just a little bit of bleed, not too much. Air entrainment for exposed concrete. So this is concrete. The reason why we have 91.7% saturation here, as you can see, is you don't have the voids fully filled. The concrete temperature is getting down, or let's call it the water temperature is getting down to 0 degrees. What happens? Water starts to freeze. You get even colder because there's a little bit of salt in that water actually. So you have to go usually lower below 0 degrees. Get a little colder. How did that happen? How did it grow? Because water expands when it starts to freeze. So that void is now fully filled with water and ice. It's a combination. Okay. Uh-oh. I don't like these lines. What happened? It cracked. Why did it crack? Because that water kept filling in the void. And eventually it was too much and it created a lot of pressure within that void and and it's trying to go somewhere. It's got nowhere to go. So it causes a lot of stress in the concrete and there's a crack and the cracks start to form. I believe water, the reason why it's 91.7, I believe is because water, correct me if I'm wrong, water expands 9%.
Yes.
I thought it was 7 too. Okay, whatever, it expands. And that's supposed to be the number just above expansion. These are what voids would look like in a concrete. So you can see that we do have entrapped air already. I think this concrete is actually air entrained too, because I do see little bubbles in there. I'm not 100% sure. I'm not 100% sure, but you can see that there are voids in concrete, right? So we developed a system to help prevent cracking. How did we do that? We added air entrainment into the concrete. It's these little bubbles that are everywhere. Right? It's only a certain percentage. Because when you get too high in that air entrainment, you start creating air that you don't want in the concrete, and I'll explain to that in a second. And also you start reducing your concrete strength. When you get too low, you don't get the amount of air that you need. When the bubbles get too big, I'll explain that in the next slides. So what happened there? Water needed somewhere to go, but this time it met its friendly air bubble in the corner here. And it had a place to go and fill that to move. And because it had a place to move, it didn't cause so much stress into the concrete and the concrete didn't crack. That's why we use air entrainment. And when the temperature starts going back up again, these start to empty out and go back into the bigger void. Until everybody's happy and the concrete isn't cracked. So this is an example of an air void filling up with ice before and after. This is the before and this is the after. So the amount of hydraulic pressure that gets formed, we don't want a lot of hydraulic pressure because it's what causes the cracking in the concrete. But how can we prevent it? How can we try to reduce the amount of hydraulic pressure that gets formed? Well, the degree of saturation is gonna help. Like we said, the 91.7. If it was 91, it wouldn't have cracked. If we can control that somehow, then we win out. It won't crack your concrete. The rate of freezing. If it freezes abruptly and quickly, you're going to get cracking again because it's just going to be too fast for the water to have a chance to move anywhere, and it's going to create pressure. Permeability. If it can travel from the big bubble to the small bubble fast enough or too slow, it's going to cause an issue with the amount of pressure that gets built up, and of course the distance to the bubble. If a bubble is close by, then it has a place to go. If it's not close by, then it's useless. And we look at this in the industry. It's called spacing factor and surface and specific surface. Specific surface is important because we actually need specific size of air bubbles to prevent to give us a well-distributed system of air. And the spacing factor is what gives us the idea of how far away it is, how far away every bubble is so that the water can travel. So we actually look at that in the industry, and there are specifications for that. Everything that is below 0.23 millimeter diameter in size, those are the airs we want. When you air entrain concrete, unfortunately, you get other stuff too, because it's not all perfect air. We also get bigger air bubbles, and that's okay. So when you're getting 6% of air in concrete, you're going to get some big and some small. Unfortunately, that's just how the game goes, because the air that gets generated is caused by friction. You don't always get the perfect air size bubble. So that's the one that we kind of target in our concrete. So why do we care about air in the concrete? Otherwise, when you walk, I'm sure you guys have all walked sidewalks and have seen this type of deterioration. That's why we care about air in concrete, to avoid this. This is happens but caused by spalling or port finishing, or it could be a few things actually. If you have the right amount of air treatment in the concrete to help avoid this. If you have to make sure that your aggregates are frost resistant, meaning that they don't fill up with water, burst, and then cause spalling. And if your concrete strength, this is an important one actually, because okay, for the first freeze, you can kind of manage that one, but the cyclic freezing, not everybody looks at this, and a lot of people pour concrete in the winter, and then they heat it for the first couple days, and then heating costs money, so they don't keep doing it. And then what happens is you get a bunch of freeze thaw cycles, and then you get sidewalks like this, and then they're going to call their construction company. Then the construction company is going to call the concrete company, and then everybody's going to have lawyers talking to each other about how we're not paying for this. And that's how it works. But a lot of it is just because they decided to take the heating off or timing or anything. Now, sometimes even if you have a perfect air system in the concrete, if your water cement ratio is way too high, it's going to break anyway, because the freeze thaw cycles are, again, it's about hydraulic pressure gets created. If that hydraulic pressure is too high, higher than the strength of the concrete, you're going to get damage anyway in your concrete. And this is another thing we want to, this is another reason why you can see it here. Forget about sidewalks. We really don't want to see that. Whoever's standing around this thing, I'd be watching out. Look at all that concrete that's starting to fall apart. We don't want that. So like we said, other advantages of using air entrainment, improves workability. It can reduce segregation because the air acts as a way for the water to prevent the water has to go around the air for it to come up, so it kind of reduces segregation. It reduces bleeding for the same reason. Actually, I was talking about bleeding there, not segregation. Segregation is, I think it's because the air helps keep up the aggregates. You could finish a little bit sooner, and it reduces the water requirements simply because it improves durability, workability. Again, salt scaling and freeze thaw is the reason why we use air, and can help improve against sulfate resistance. This is moving on to what we were talking about earlier about net zero 2050. We're trying to get concrete at a lower CO2 content so that we can achieve the 2050 goals that the government of Canada has come out with. So there is an action plan in place. Here's kind of a breakdown of where CO2 comes from. The raw material itself produces a certain amount of CO2, is about 80–85% from out of the concrete plant. Then you've got raw material transportation. You got to move that material from the quarry to the plant, and the plant to the job site. So that's all part of that. And then there's a whole bunch of electricity, gas, and so forth and so on that you need to take into consideration. GU per ton creates the most amount of CO2 in the concrete itself. You can see it's considerably high. The GUL does reduce it a little bit. Slag reduces it even further. So if I can replace all of this cement by slag, you've already reduced your CO2 content by, what is that, 6% or 6 times, 5 times. So that's pretty considerable. Aggregates have nearly nothing for the amount that goes into the concrete. Fly ash, nearly nothing, and then so forth and so on. Admixtures, nothing. Water, pretty much nothing. I mean, if we get these down to 0, then you could say these are something. But until then, the 5 C's of sustainability. They're looking at ways that they can try to reduce the amount of CO2 that is created when developing clinker, which is what I talked about. The high temperatures are really what is causing that CO2. The cement itself, trying to replace the cement with different types of other cements. Concrete, trying to find ways, even new types of cements that are in the works will help reduce the CO2 in the concrete. Construction is all about design. So for example, if for concrete, if you could find a way to reduce the size of the concrete and volume that you're using, you can end up reducing the CO2 of the project itself. So that's also a pretty key thing to keep in mind. Carbon uptake is how do we take carbon from the outside world and shove it into concrete so that it almost works as a counterbalance. I've captured some of that carbon rather than let it just making it. And this is how we kind of look at reducing all those values there, like we just talked about. Mix optimization is pretty key. Reduce the cement content, try to use as much SCMs as possible. Add mix is a big one. If you can create stronger concretes at higher water cement ratios without too many issues, then you're reducing the amount of cement. Really, the game is about reducing cement because that's the biggest contributor. And then innovative new materials that are coming out. Like I said, graphene is one of those ones that they're looking at to help do that. This is the goal that we were talking about. So they want net zero by 2050. 2030 was supposed to be half. I'm not sure why it's 4 here, but that's what I understood it as. And there's manufacturing and transportation, how that breaks down. And clean energy just means, for example, there's some ideas, for example, a concrete truck works off of diesel today. So that truck that delivers the concrete, they use diesel to power it. Why not make it electric? Why can't Elon Musk come up with an electric? It'd be pretty cool if he did. An electric truck. And trust me, they're all thinking about it. All those 2 more minutes. Okay, I'm almost done. This is just a guide that has been developed by the Ready Mix Concrete Ontario, which highlights how to specify for low carbon concrete. And it's already out there. If you guys want to look it up online, you can go through it. It's very interesting. This book is it's probably a book you guys have seen if you're taking a concrete course. I have the 7th edition. This is the 9th. I still use it today. I go back to it, reference it all the time. It's a really good book. And you can actually order it online. I don't know why I'm the one telling you to go do that, but if you want to, it's a good book. So before we move on to the next questions, I'm just going to go into the ACI stuff. How do we do? Is it control fire? No, that wasn't it. I think I just did something like I didn't get closed. It's only 2 minutes or so. Oh, there we go. So ACI, what is ACI? It's the American Concrete Institute, and it's a chapter. There's a chapter here in Ontario, and these are all the things we govern here in Ontario. So you'll see that you guys. We help with scholarships. We do quite well with recognition in terms of awards and such. And we do sponsor teams. Anyone here from the concrete too or toboggan? Yeah. Okay. You dealing with Frank at all? No? That name doesn't sound familiar? Okay. We help sponsor and contribute to a bunch of different sponsorships and such in the industry. This is how it breaks down. I'm the president. There's a bunch of other people on there. These are the sponsors for ACI, the main sponsors in the industry. This is kind of our function. We help do concrete field testing technician. We help with the standards in order to get you certified for self-consolidating concrete or concrete field technician or flat work, depending on what you're looking for. We have webinars and dinner meetings where we go through things like high performance concrete, tunneling, low carbon future of cement and concrete industry. That was an interesting one. I was there. Underground construction, for example. We talk a whole bunch of things that the industry is concerned with, that they're interested in, and we got lots of people showing up. And it's quite they're quite good, the webinars. You can go on our website to take a look at what's coming next. We do site tours where we'll go see a cement plant or a precast plant, and you actually see how those things function in real time. We have a seminar coming up. It's a full day seminar, Lobster Fest, where we go through, you like that? I'll see you there then. We go through state of the art, for example, concrete durability design. We really talk about topics that the industry is interested in. And if you're in the industry and you're dealing with concrete, I would advise you come to these things because first of all, you get to know people in the industry and you get to find out what people care about. And then at the end of it, we have a lobster fest and pig roast. So you can stick around for that too if you want. In 2025, we have in Toronto's hosting the International ACI Convention. It's a big deal. Lots of people come. This is why it's a big deal. Lots of people come to it from all over the world, actually. ACI is not just in America, it's in Canada, it's in Australia. Anywhere where they use the American standard, it's there. I think the Philippines, there's a whole bunch of different countries that end up using ACI, and they'll end up showing up to this conference themselves. And it's a pretty big one that's coming up. Lots of topics are going to be discussed. There's a networking for students. There's student competition. For example, you're gonna have to design a bowling ball that's fiber reinforced. Things like that are coming up, and I would advise that you look into it. It's on our website, and it's coming up March 30th to April 3rd, 2025, and we're hosting it. Hasn't been hosted here in a long time, so we're hosting it here in 2025, and that's it.
I actually learned a lot, so that was great. Thank you so much. We won't have time for questions from the audience.
Okay.
But please feel free to come by afterwards. Because I know a bunch of them have to get to class. So once again, thank you so much.
Thank you.